Okay, good morning. So, I don't know, how's your summer? Is it going well? Yeah, good. Okay. So, if you remember, we talked about prepositions, and today I want to talk about predicates and quantifiers, because usually in mathematics, of course, I can say 2 is a prime number, that's a preposition, but usually we want to work with sentences like that. If n is a prime number, then what? So in principle, we have some variables in the sentences that we use in mathematics. Okay, so that's the motivation behind the notion of predicates. Okay, so let me just define it for you. So a declarative sentence, again declarative, that expresses a property regarding one or more variables is called a predicate in that or those variables. A predicate P regarding the variable x is generically denoted by Px or sometimes by P of x, putting it in a pair of brackets. So usually in principle you really don't need to put a pair of brackets around the variable, but sometimes it's easier for us to read, so we use a pair of brackets around them. And by the way, as usual, these notes, the PDF of these notes will be below the video on YouTube. Okay, so you can go to the description and download it if you want. Okay, is that understandable? So the preposition, so what a predicate has in common with a preposition, both of them are declarative sentences. Okay, for example, let me just give you a simple example. If I say that x is a prime number, of course, it's a declarative sentence. It is an assertion about the variable x, but this is not a preposition. Why? Yeah, because a preposition should be either true or false, but not both. But we cannot say if it is true or false. Yes, because we don't know what x is. So it's asserting something. It's a declarative sentence about x, but I cannot call it a preposition because I don't know if it is true or false. And it doesn't matter if I am more knowledgeable, if I become more knowledgeable or not, there is no way for me to understand that x is a prime number because the value of x is not given to me. Okay, but these kinds of sentences are ubiquitous in mathematics, so we call them predicates. And then, for example, I can say that this is predicate with variable x. Okay, but the problem is that if I replace x with some value, then it becomes what? A preposition. For example, if I say P of 3, or it means 3, I'm replacing x with 3, is a prime number. Okay, so this is a preposition. And in this case, this preposition is true. For example, if I have P of 9, then it becomes 9 is a prime number, which is a false statement. So a predicate is a declarative sentence. It can transform to a preposition if you replace the variable or variables instead the predicate with values. Okay, and these values that I am replacing the variable with them are coming from a set. I'm using the notion of set here. In principle, I am not allowed to use the notion of set right away, but I am just counting on your knowledge of set theory as we studied in Math 5. Very baby set theory, okay? So the set containing all possible variables that I can use for the variable of the predicate is called the universe of discourse. Okay, the universe of discourse. Okay, so is that more or less understandable? But of course, I can have much more. I can have more than one variable here. So let us go back to the notes here. So for example, consider the following sentence. I have written this one. X is an irrational number. Okay, this is a declarative sentence. It is not a preposition yet because I see the variable x. There is no way for me to say if it is true or false. So it is not a preposition, but it is a predicate in variable x. Okay, this is a predicate in one variable x. We can symbolize this predicate as p of x. In this case, p of the square root of 2 means what? Refers to this sentence. Square root of 2 is, I should have mentioned, an irrational number. Sorry. So this is a very big mistake, because in principle I have to just take x out and replace it with that number, changing nothing. So I was a little bit careless here, sorry. So I should have written a square root of 2 is an irrational number, and p of 3/4 will be 3/4 is an irrational number. Of course, in the first case, it is a true statement or a true proposition, and in the second case, it is a false proposition. So that was not a good example, sorry, but you have to be careful. Just replace the variable with the given number. Okay, so now let x and y be real numbers. Consider the following sentence. X is less than y plus 2. Okay, so that you see, it's a declarative sentence again, including two variables, one x, the other one y plus 2. So this is a predicate in two variables, x and y. Okay, for example, let me denote this by lxy. Yes, you can write it as L parentheses x and y. Yes, the reason that I am trying to give I don't know how much complete we want to do the logic, because might be we go like a spiral, because if you want to study logic, we can continue studying logic by the end of our lives. Yes, so but the problem is that I want to get rid of the logic and go to the next step. Might be we can come back and complete it like a spiral in a higher level. We go round and then in a higher level. But anyway, so you can write it as lx and y, lxy. It doesn't matter. If you like this one, use this one. If you don't like, we can use this. Okay, so let us go back here. So in that case, when I write L51, what does it mean? It means that replace x with 5, replace y with 1, and read the sentence. So it becomes 5 is less than 1 plus 2. Is this a proposition now? Yes, because it is claiming something, and it is either true or false, but in this case it is false. And then you can write L15, which you have to replace x with 1, y with 5, and read the sentence, so it becomes 1 is less than 5 plus 2, which is in this case a true proposition. Is that right? So it's not hard. Okay, so let us see what we have now, and then let me just formalize it again. When dealing with predicates, the set from which the values of the variables in the predicate are chosen is called the universe of discourse of the predicate. But be careful about this point as well. If the predicate depends on more than one variable, then the universe of discourse of each variable might be different. Yeah, so you can choose different universes of discourses for different variables in the predicate. Okay? Any questions so far? Okay, so let us go to the next. Now, this is the most important thing that we want to study today. So the phrase for all is called the universal quantifier and is denoted by this upside down letter A. Yes? And the phrase there exists is called the existential quantifier and is denoted by this symbol. It is like E, capital E, but in the reversed order, in the reversed form. So when you see for all x px, yeah, read it like this. So this symbol is read for all x px, or p of x if you use the pair of brackets around it. And when you see this, you read it as there exists an x such that px. Okay, so this means that, of course, some people read it that there exists at least one x. That's also correct. But there exists an x such that p of x. So these are called universal quantifiers and existential quantifiers. Okay, so now my question for you is this. You think a little bit here. So if px is a predicate, so it is not a preposition yet. But when I write for all x, by the way, here when I say for all x, I'm assuming that the universe of discourse has at least one element for which P of x is true. Okay. But when I write for all x px, my question for you is that, what do you think about this? Do you think it is a predicate or a preposition now? Yes, it's a preposition. So you see P of x, so if you just read it here, x is a prime number. You cannot decide about the truth value of this assertion yet. But for example, let us choose the universe of discourse to be the natural numbers. And when I say for all x px, then it means that for all natural numbers x is a prime number. Now, do you think it's a preposition or not? Because immediately I can judge about the truth value of this sentence now, which in this case is false, because there are a lot of natural numbers that are not prime numbers. So you see, when we use quantifier on a predicate, we are transforming the predicate to a preposition. So usually you can view it in this way. Quantifiers are tools in our hands to turn predicates into prepositions. Okay, for example, if I have the same sentence and I write there exists xpx, do you agree that this one is also a preposition now? This is claiming that there exists an x where, because I have chosen the universe of discourse to be the set of natural numbers, this tells you that there exists a natural number such that x is a prime number, which in this case is true. So you see that this is now a preposition. Is that understandable? So have this in mind. If someone asks you why quantifiers are useful, quantifiers are a tool. The quantifiers are tools that we can transform a preposition, predicate to a preposition. Yes.
I'm sorry, I can't miss what the universe of discourse was. That was like the set of elements.
A set of elements that we can choose the variables from that. Yes. So of course, this, for example, the universe of discourse can be the set of all humans or whatever.
But it also applies for just normal predicates.
Yeah, it's like a source,
No.
a reservoir for taking the values from, taking the values of the variables from. Yes. Okay. Any questions so far? Is that understandable? Okay. And something like this is important to know. This variable that you see here is a dummy variable. Yes. This is a very nice terminology we have. I don't know, dummy variable. It means that if you replace the name of that variable everywhere to something else, the sentence does not change. Yes. For example, I can say for all y, py. Mathematically speaking, there is no difference between this preposition and that preposition. I have changed the name of x everywhere to another letter y. Yes, is that understandable? So this tells you that there exists, so this tells you for all x in the set of natural numbers, x is a prime number. This is also telling you the same thing. This means that if I want to translate it in plain English, how do you say this?
For all
no, plain English.
Every natural number is a prime.
Is a prime number. And what if you write this in the plain English? That's the same thing. So I just want you to understand changing the name of the variable. If you change everywhere the name of the variable, it does not change. So that is, are you familiar with dummy variables in other parts of mathematics as well?
Well, I mean, what kind of variable is the dummy variable? I mean, you can call any number, like variable x or y or alpha or...
No. That's a good question, because all of those, for example, if you are right, this is a dummy variable, do you know why? For example, if I write this, that's a very good question actually. Are A and B dummy variables here?
Yeah,
why they are dummy variables? Of course, if I want to write, this is, by the way, is it a preposition? No, because it contains variables, yes, and we don't know if it is true or false. So we have to say for all A, for all B, if the universe of discourse is R, for all A, for all B, this is the case, then it becomes a preposition. Okay? Okay, so in that case, I am using the same idea, but Is there any variable that is not a dummy variable?
I mean, it's kind of like the definition of a variable. It's like a placeholder.
No, actually, it should be a different thing, you know. Uh, in principle, I wouldn't say, for example, if you have integral of x squared dx, what is the answer? The answer is x cubed over 3 plus a constant, yes? But if I write integral of y squared dy, then it becomes y cubed divided by 3. You cannot say y here is a dummy variable, because if you have both of them in the same problem, and then we are insisting to use different variables, it means that, of course, x and y can be equal, but there is no guarantee that x and y are equal. So I would say that not every variable is a dummy variable. But if I make it a definite integral, then it becomes a dummy variable. So for example, if I say integral from 0 to y x squared dx, what's the answer? The answer is this, running between 0 and 1, which is a third. And now if I replace this with y or any other variable, of course it becomes y cubed over 3, and then run it from 0 to 1, then it becomes 1/3. So that's a dummy variable, okay? Is that right? Okay, anyway, if you don't like this, forget about this. But anyway, we can change the name of the variable from any letter. If I respect that I'm changing every occurrences of that variable to a different variable, I am not changing the preposition. Yes? Okay. So that's one thing that I want you to mention. I want to mention. Another thing is that I want to talk a little bit about, you see, we started with propositional logic. I haven't presented the logic in a very formal way. Might be I can spend one lesson in the future to talk a little bit about logics in formal way. But if I want to categorize that, we had propositional logic, and then when predicates come in, we say this is a first order logic. So a logic that a propositional logic, if I add these two quantifiers to propositional logic, we say that we have the first order logic, okay? And we also have second order logic. Second order logic, I just want to tell you a little bit briefly about that. A second order logic is that you can use quantifiers on properties. Okay, so I'm using quantifiers here are from elements of the universe of discourse. Okay, so I can say these are atomic variables. Okay, but I can use quantifiers on properties. If a quantifier is used on a property, that sentence that we have is a sentence from the second order logic. So for example, I don't know if I can give an example. So you know that, let me just give you a little bit of example from number theory. So you know that if A, so let us say that A, B, and C are natural numbers. If I say that A divides B, C, we learned this in Math 5, yes? So if A divides a product of B and C, do you think I can conclude that A divides B or A divides C?
Yes.
Be careful.
I mean, it divides one of them, at least.
So if in that case you are saying that this implication is true for all
No, never mind.
A, B, and C in N. I'm using this, okay?
No, I don't know what I'm saying.
Of course, no. Yes, because for example, if you have 6 is dividing 1 times, so let me write 2 times 3. Yes, this is a true statement because 2 times 3 is 6. 6 is divisible by 6, so this is true. But is it true that I say 6 divides 2? No. Is it true that 6 divides 3? No. But it turns out that there is some property so that if A has that property, this is true. Can you guess what that property is?
Equal to previously.
No, there is a property that if you say if A has that property and A divides B and C, then you really can conclude that A divides B or A divides C.
If it's a prime.
It's a prime. Okay, so being prime is a property. Okay, so we can write there exists a property. There exists a property so that for all x Let us choose the universe of this course to be n. Of course, n and all possible properties, because I'm using quantifier on a property, yes. So there exists a property such that for all x and for all y, yes, so yes, for all p, if q of p, and for example, I can say p divides xy, then p divides x and or p divides y. Yes? Something like that. So this tells you that there exists a property so that for all x and y coming from the set of natural numbers and for all p coming also from the set of natural numbers, if p has property q and p divides x, y, then p divides x or p divides y. Okay, so you see that this is a little bit different of a structure. I just want to give you a feeling, yes? I am using the quantifier not on an element as before, but on a property. So if you are using quantifiers on properties, that is the topic which we call second order logic. Yes?
This is also a proposition.
Pardon?
And this is also a proposition.
What do you mean proposition? Yes, at the end it should be a proposition. Yes. Yes.
We will go over this later.
I don't know, but let us. Yeah.
I shouldn't write this down.
Yeah, it's not bad to write it down, but at least I want to spend one lesson probably on formal logic a little bit. That's good to understand. But I just want you to understand there is a difference between how I am using quantifier here and how I was using quantifier there. So if you don't have any quantifiers, that is called propositional logic. If you add quantifiers, then you have first order logic. But if you add if you can apply quantifiers on functions or on properties, that is called second order logic. Okay, so that is just a little bit of information I wanted to have. So now let me ask you another question so that we can finally go to some examples. Yeah. So what do you think here? If I have a predicate with two variables, x and y, okay. By the way, let me also give you a name. I will, of course, formally introduce them in my slides. If you have a variable coming immediately after a quantifier, that is called a bound variable. Okay, so this variable, and that was bound variable. Bounded by the quantifier. I will have these slides, I will show you. Okay, but now, if the variable is not bound, it is called free. These are the terminologies I want to make it easier to talk about, to refer to when I am talking and teaching. Okay, so this is a bound variable. This is, I haven't, so here you don't have any free variables. But for example, if I have this one, for all x, pxy, then x is the bound variable, bounded by the universal quantifier. Do I have also a free variable? Y is a free variable. But let me ask you one question. If I ask you what the structure of this is at the end, what do you say? It's a predicate. Is that right? It's a predicate, but a predicate in which variable? Y. So if I want to give it a name, I can call it Q of Y, for example. Or if you want to say the same notation, I can just write QY. So here, Y is a free variable. So it means that I am using the quantifier on X, but Y is free. Okay? So this is no longer a proposition because there is still another variable left. I can call it something depending on Y, so it is Q of Y. But now if I write Q of 3, how can I write this? Q of 3 means that I am substituting the free variable Y with the number 3. So let us say that 3 is in the universe of this course. So this becomes for all px and 3. So let me write it like this here. So I want you to understand the structures, yes? Is that clear? So for example, if I have for all x, for all y, p, x, y, and z, and t, okay? So what are the free variables? Z and t, what are the bound variables? I can also write, if you want, let me change it to existential here. So for all x, there exists a y, so that p, x, y, and z, and t. So if I want ask you, is this a preposition? No, it is a predicate. But predicate in how many variables? Two variables, z and t. Yes, so I can, for example, call it q, z, and t. And when you have free variables, in principle, you can do the substitution. So you can take those variables and replace them with any value from the universe of discourse. Then in that case, you have a proposition at the end, after all substitutions are done. Yes.
So the for all quantifier, the universal quantifier, that's only from the universal discourse, right?
All of them.
No, so like for all x, then that's only the x in the universal discourse, right?
Yes, yes, yes.
So for every
Always, always.
Yeah.
If I don't mention explicitly, yes, always these are coming from the universal discourse. Yes, so is that clear now? Okay, so now let us go to slides to see if I have more exercises. We'll consider a proposition including one or more quantifiers. Any variable that comes immediately after a quantifier is called a bound variable. Any variable that is not bound is called a free variable. Yes? Okay, now we want to do this exercise together. So let n be the universe of discourse and let p of x is a prime number, ox, x is an odd number, dxy means x divides y. Okay? Determine the truth value of the following propositions. First of all, let us just concentrate here. Do you agree with me that this is a proposition? Can you understand it deeply? Yeah, I mean, yeah. Why for? So let me just write it here. So for all x, I have written px qx. So let me ask you one question. If I just ask you what this is, what do you say? It's a predicate, yes, because if I replace x with some value, then it becomes a conditional. So it is not a statement, it is not a preposition yet, but if I replace x with any given value, then it becomes a preposition, and I have a preposition in front of the universal quantifier. So it is at the end a preposition again. But this part of it is a predicate. Okay, so going back here, and so is x bound or free? Bound. Yes, let us go here. Can you see that this is also, is this a preposition or a predicate, number 2? I have written in the text that this is a preposition, but can you see that? What is x and what is x is a bound variable because it comes immediately after existential quantifier, and y is a bound variable again because it comes after the universal quantifier. Okay, so I hope that you see this structure. I want to go through it yourself and determine if they are true or false based on what you have previously in mathematics.
The universal discourse is still natural numbers.
Yes, I have written n. Let n be the universe of discourse.
Define the universe of discourse like Jerusalem said.
Sometimes they use the curly u, something like that. But to be honest, I don't know if this is standard or not. Okay, so could you come up? So how do you read this in plain English? So P of x means x is prime, O of x means x is odd, the universe of discourse is the set of natural numbers. Can you read it in plain English? Yes?
All prime numbers are odd.
Yes. Yeah. For every x in the set of natural numbers, if this is the case, it means if x is prime, then x is odd. But of course, this is a little bit robotic way of reading. But if you want to read it in plain English, you say that every prime number is an odd number.
But, I mean, you would more have to say that if a number is prime, it's odd.
Yeah, something like that. Yeah, but this is also correct, what Rasmus said, I think.
Yeah. But I mean,
I would prefer that
yeah.
if I want to write something, but of course you are also right. So is this true or false?
That's true.
False.
False.
It's false.
Yes. Why? 2. Yes, because of 2. Yes. 2 is prime, but it is not odd. Yeah. So anyway, this is a false statement exactly because of one counterexample, and you know already about counterexample. We talked about this a lot in math. Why? Okay. So that is a false statement. Yes, because 2 is prime but not odd. Okay. So what about the second sentence? Can you read this in plain English?
There is a prime that divides a number greater than 2.
So, if I want to read it a little bit robotic way, how do you read it? For every natural number, if the natural number is greater than or equal to 2, then there exists a natural number so that that natural number is prime and x divides y. Okay, but how do you read it better? I would say for every natural number greater than or equal to 2, okay, there exists a natural number such that there exists a prime number. That's a better way of reading, yes? There exists a prime number so that there exists a prime number x so that x divides that natural number.
So for every prime greater than 2, greater than or equal to 2, there is another number which divides it.
Okay, anyway, this is a true statement or false?
True. We'll say false, but
I mean, because why is it prime?
I don't have much confidence after the first one.
No, yeah, I don't think it should be hard. So let us make sure that you really understand. I want you to come up with the decision, the decisive decision. Is it true or false? There is a name for this. This is a theorem, yes? Isn't it the fundamental theorem of number theory, yes? So you know that every number can be factorized into prime factors, but that is not the fundamental theorem of arithmetic. The fundamental theorem of arithmetic is that if you have a natural number greater than 1, which means greater than or equal to 2, definitely there will be a prime factor for it. Yes. So any natural number greater than 2, greater or equal than 2, has a prime factor. That is exactly the fundamental theorem of arithmetic written in mathematical language.
Because x itself can also be y, right? Or equal to y.
Yes, yes. Is that understandable? So this is true. It tells you that if you choose any natural number greater than or equal to 2, you can find a prime number that divides that natural number. That is fundamental theorem of arithmetic. Yes?
So is a proposition like this, is it always a contradiction or tautology? Like is there only...
No, this is a proposition.
Yeah.
It can, so...
Okay, but can it be, like, can it have different truth values based on the variables, or...
Yes. No, here this is a proposition. This one is either true or false.
Okay. So
no, tautology makes sense when you have predicates. When you have prepositions that you don't know if this is true or false. So you're combining. So this one, if P then Q, we can talk about if this is a tautology or not. If it is going to be tautology, it means that for any assignment, any truth value assignment to P or Q, this becomes true if it is tautology, or it becomes false if it is contradiction. Okay?
Yeah.
Yes?
Yeah, but so like, for example, in the first...
no, this don't confuse. This is a proposition.
Yeah.
So it is either true or false.
Yeah.
Yes?
Yeah.
Of course, if it is true, you can say it is a tautology.
Yeah, well, okay. So
yes?
More like, it doesn't matter. Like this, the truth values of these can't change if you change the variables.
Yeah, so this truth value, yeah, that's the problem. Usually the notion of tautology comes in when you have freedom of choosing truth values for these components, yes? Okay. So is that understandable? Okay, so let us go to the next example. Okay, I want you to think a little bit about that. Suppose that all of the following propositions are true. This is the assumption. For all x, px or qx, for all x, if Rx, then not Qx. Number 3, there exists an x such that not Px. These 3, I am telling you, assume that all of them are true. What can be said regarding the truth value of there exists x not Rx? Okay, so I want you to think about this. The assumption is that these statements are all true. Based on this information that I am giving you, I want to explore if something decisive I can say about this statement. I hope that you see that all of them are statements, yes? Because I have only one bound variable, so all of them are prepositions now, so that's also preposition. I just want you to think a little bit about that yourself. Okay, so what do you think?
I think it's true.
You say that this is true, okay? Anyone else? Opinions? True? Okay, so how can I understand that this is indeed true? How did, yes?
So the last true statement that you gave says that.
Is it P?
Yeah, P.
Yes, okay.
So it says that there exists one case, at least one case, where not Px is true, and according to our first statement, either Px or Qx have to be.
Okay, so you started wisely from the last one because that was also my intuition. So you're starting with the existential quantifiers better. So what is the claim here? The claim here is that there is at least one element from the universe of discourse for which this is true. Okay? Not P of x is true, so it means P of x is false. But let me just tell you that because there exists, let me give this a name. So this means that is true. This implies that there exists an element from the universe of discourse for which this is true. So let us give this a name. Let me x naught be that x for which not px naught is true. Okay? And then this means that p of x naught is false. Okay? So this is the conclusion that we have. So it means that there exists an element in the universe of discourse which I give it is the name x naught, for which px naught is false. Okay, but which one now you want to use? It is good to jump here. Yes, this claims that for any element from the universe of discourse, including that particular one, this statement is true. So because this statement is true for all elements from the universe of discourse, can I conclude that px naught or qx naught is true?
Yes.
Yes. Because this tells you that for any element from the universe of discourse, this should be true, including that particular element x naught. So I know that px naught or qx naught is true. But on the other hand, I know that px naught is false, and the disjunction is true. So what can I conclude from here? That qx naught is true, because if qx naught is also false, false or false is false. Yes? So this is the conclusion that I have so far. Okay. And now what do? I go here. This is also claiming that for any element from the universe of discourse, including this element, this statement is true. Yes? So I know that if Rx naught, then not Qx naught is true. This I know. Yes? And then I know that the conditional is true if what happens? So if this is true, what can I conclude? You see, qx naught is true. So this means this part is false. So can this be true? No, because if this is true and this is false, the conditional is false, but I want to have it true. So this means that what can I conclude? This one, together with this one, I can conclude that what happens? R of x naught is what? Is false. Yes? But if Rx naught is false, what can I conclude about the negation of Rx naught? It's true. Okay? So I know that negation of Rx naught is true. And what this claims? This claims that there is an element at least in the universe of this course for which negation of Rx for that x is true. So this means that this statement in general, in this case, is true. Why? Because I was able to find an element x naught from the universe of this course for which this statement, this predicate turns to be a true statement. Yes, that's cool. Is that understandable? Yes or no? Okay. So if you don't mind, let us have a rest here for 5 minutes and then we come back, okay? Any questions here? Okay, so we have a little bit of rest, 5 minutes, and then we start again.